Last year, there was this Fortune 500 company, right? And they had to scrap over $1 million worth of custom printed circuit boards,
Oh, wow. $1 million just in the trash.
literally in the bin. And, it wasn't because of a catastrophic manufacturing defect. It wasn't like a shorted power plant or anything like that.
Right, which is what you'd usually expect with a scrap that huge.
Exactly. The reason they had to trash an entire production run was a 50-cent 8-bit microcontroller.
A 50-cent part. That is just brutal.
It really is. Because on paper, according to the datasheet's high-level summary,
Yeah.
the chip was perfectly spaced for the job.
Right, the glossy front page of the datasheet that promises the world.
Yeah, exactly. It had the right number of pins, the right clock speed, the right serial ports. But what the hardware engineering team missed, and what the firmware team didn't catch until the boards were literally already back from the fab, was that this specific chip lacked a direct memory access controller, a DMA.
Oh, man, without a DMA, you're dead in the water with high-speed data.
Completely. The CPU was forced to manually process every single byte of incoming high-speed sensor data.
Which means it's just drowning in its own interrupt requests.
Right. It was utterly unable to execute the core application logic. So, welcome to the deep dive.
It's a brutal story, but honestly, I mean, it happens constantly in this industry. $1 million gone because of a missing hardware peripheral that was, probably a footnote on page 400 of the reference manual.
And that is exactly why we are here today.
Mm-hmm.
We are looking at a massive stack of sources you've provided, hardware teardowns, silicon vendor data sheets, and some truly fantastic embedded engineering manifestos.
Yeah, there's some really great material in there about the actual realities of production.
Definitely. And the goal is to figure out how to navigate the absolute minefield of microcontroller selection. I'm coming at this as a hardware design engineer,
Right, the tactile world.
Yeah, my world is entirely tactile. It's governed by physics.
Mm-hmm.
I'm obsessed with PCB layout, routing differential pairs, managing parasitic capacitance, and dealing with the sheer thermal realities of silicon.
And, well, I approach this from deep in the trenches of embedded firmware and real-time operating systems.
This software side.
Exactly. I'm the one who has to take your meticulously routed hardware and write the bare metal C and C++ code that actually forces it to behave deterministically.
Right.
If you pick the wrong chip, my firmware either crashes or, I spend 6 months writing assembly code to patch over your hardware deficiencies.
Okay, fair enough. So the mission today is to build a framework for you, the listener. We want to take you, assuming you already have a solid foundation in electronics and you're staring at that DigiKey search page with like 90,000 variants of microcontrollers.
Which is overwhelming for anyone, really.
It's completely overwhelming. So we want to take you on a journey from making hobbyist guesses to applying rigorous, professional, industry-level decision matrices.
I love it.
But before we get into the 10-step selection framework, let's just establish the foundational atom we are talking about, the microcontroller, the MCU. Let's trace it back to the split in the evolutionary tree, right around 1971 with the Intel 4004.
Right. The 4004 was brilliant. It was delivered to Busicom for their calculator.
A 4-bit bus, right?
Yeah, 4-bit bus running at a blazing 0.74 megahertz. But the thing is, the 4004 was a microprocessor, an MPU.
Okay.
It was the start of one branch of the tree. The true paradigm shift for embedded systems, the actual birth of the microcontroller, came a little later in 1974 with the Texas Instruments TMS-1000.
Right, and the sources emphasize this distinction incredibly heavily. The DMS-1000 ran at, 0.3 megahertz with just 1 kilobyte of ROM and a tiny sliver of RAM.
Barely anything by today's standards.
Barely anything at all. But the revolution was the physical integration. I always think of it using a variation of the Swiss Army knife analogy our sources suggest, but looking at it from a PCB layout perspective.
Okay, lay it on me.
Well, a microprocessor, an MPU, like you'd find in a desktop or, say, a Raspberry Pi, is incredibly powerful. But it's like a sprawling planetary colony.
Right, it needs infrastructure.
Exactly. To make the CPU function, you have to route highly sensitive, high-speed memory buses across the green fiberglass of a motherboard to external DDR RAM chips. You need external flash storage.
You have to deal with all that complex routing.
Yeah, trace length matching, impedance control, massive power delivery networks, just to get the system to boot.
What's fascinating here is that the MPU relies entirely on a sprawling external supply chain of peripherals.
But microcontroller, the MCU, is the ultimate Swiss Army knife. Or, maybe more accurately, it's a completely self-contained orbital habitat.
I like that.
It takes the processing core, the SRAM for variables, the flash memory for the executable code, the oscillators for the clock tree, and all the input-output peripherals, and it fabricates them onto a single monolithic piece of silicon.
And, the firmware implication of that physical integration is profound.
House.
And, the firmware implication of that physical integration is profound. An MCU doesn't need a heavy, complex, generalized operating system like Linux or Windows to manage vast external resources.
It doesn't have to wait for an external hard drive to spin up.
Exactly. It wakes up from a power-on reset, fetches the very first instruction from an internal hardware address, and executes its dedicated task immediately.
Right.
It provides a level of highly reliable, deeply deterministic behavior that a general-purpose processor simply cannot match.
So we have this highly integrated silicon block. But when you open a distributor website to buy one, you are immediately hit with the first major architectural fork in the road.
Ah, yes. Von Neumann versus Harvard memory architectures.
Right. In a von Neumann architecture, the chip uses a single unified memory space and a single physical data bus. The program instructions and the actual variable data share the exact same microscopic silicon highway.
Which fundamentally creates the von Neumann bottleneck.
Explain that for me.
Well, your instruction to, say, add these two sensor values and the actual sensor values themselves have to take turns traveling down that single bus.
Okay, let me push back here. As a hardware guy, die space on a silicon wafer is incredibly expensive.
Absolutely.
So routing two completely separate parallel internal buses, meaning twice the address lines, twice the data lines, takes up valuable physical real estate inside the chip.
It does.
So why go through the physical hardware trouble of building a Harvard architecture? Why do our sources say that modern microcontrollers predominantly use Harvard or, modified Harvard architectures?
Because of the fetch and execute overlap.
Okay.
In deterministic embedded systems, we just cannot afford to wait. If you only have one bus, the pipeline stalls.
Because it's waiting in traffic.
Precisely. The CPU fetches an instruction, it decodes it, then it has to wait an entire clock cycle to go back out on that same bus to fetch the data.
Right.
Desktop CPUs solve this von Neumann bottleneck by throwing massive, power-hungry L1 and L2 caches at the problem.
But in an MCU?
Right. In a highly constrained MCU running on a coin cell battery, you don't have the silicon area or the power budget for megabytes of cache.
So you separate the physical highways.
Exactly. With the Harvard architecture, the CPU can fetch its next instruction from the flash memory bus while it is simultaneously reading or writing a variable to the SRAM bus.
Oh, wow. So they happen at the exact same time.
Yes. It guarantees single-cycle execution for many operations, which is absolutely critical for digital signal processing, like filtering audio or controlling a high-speed motor.
That makes total sense.
Furthermore, because the buses are physically separate, they don't even have to be the same width.
Wait, really?
Yeah. You can have a 16-bit wide instruction bus fetching opcodes, while an 8-bit data bus handles the variables. It's a hardware optimization that directly translates to predictable firmware execution times.
That perfectly frames the next major architectural choice on the selection matrix: bit widths and instruction sets.
Right.
Because the 90,000 chips out there are broadly categorized into 8-bit, 16-bit, and 32-bit cores.
And the bit width essentially defines the width of the internal registers and the arithmetic logic unit.
Okay.
It determines how much data the CPU can process in a single chunk.
Right. And an 8-bit microcontroller, like the classic Microchip DIC or the Atmel AVR, is the absolute bedrock of the industry.
Oh, for sure. They are everywhere.
But wait, if 32-bit chips are incredibly cheap now and can address gigabytes of memory, why are 8-bit chips still shipping by the billions? I mean, why hasn't the 8-bit architecture gone the way of the floppy disk?
It comes down to interrupt latency and architectural simplicity.
Okay, unpack that.
An 8-bit AVR has virtually zero pipeline complexity. There's no branch prediction, no speculative execution.
It's just simple.
Very simple. When a hardware interrupt fires, say, an optical encoder on a spinning motor triggers a pin. The 8-bit chip stops what it's doing, pushes a tiny context to the stack, and jumps to the interrupt service routine in exactly 3 clock cycles.
Wow, every single time.
Every single time.
Absolute determinism.
Yes. Whereas a modern 32-bit ARM Cortex-M4, which has a multi-stage pipeline, well...
That's going to take longer.
Right. It might take 12 to 15 clock cycles just to push all its 32-bit registers to the stack before it can even start executing the interrupt.
So for simple tasks, The 8-bit is actually faster to respond.
Exactly. If you are designing a simple, safety-critical relay controller or a basic temperature monitor, that 8-bit deterministic response, combined with the fact that it draws microamps of current, makes it vastly superior.
But the moment you need to do heavy math, the 8-bit falls apart.
Completely. If you ask an 8-bit chip to multiply two 32-bit floating point numbers, it has to break that down into hundreds of tiny 8-bit operations.
Oh, man. That sounds painful.
It is. It takes hundreds of clock cycles. A 32-bit chip with a hardware floating point unit does it in one cycle.
One cycle. That's a massive difference.
That is why the industry has massively shifted to 32-bit architectures, dominated by ARM Cortex-M, and increasingly the open-source RISC-V ISA for anything involving the Internet of Things, network stacks, or edge AI.
You mentioned ISA, the instruction set architecture. Our sources detail the historical battle between CIC complex instruction set computing and RISC reduced instruction set computing.
It's an important distinction that directly impacts your memory floors.
That's
RISC architectures, like ARM, focus on executing highly simplified instructions where almost every instruction takes exactly one clock cycle.
okay.
CISC, on the other hand, allows for highly complex instructions that might take multiple clock cycles to complete.
But wait, if RISC is faster and more power efficient, why would anyone ever architect a complex multi-cycle instruction?
Code density.
Okay, explain that.
Historically, and even in highly constrained environments today, internal flash memory is incredibly expensive.
Right.
If you can write a complex memory-to-memory mathematical operation in just a single 16-bit word of compiled CISC assembly mode, you save precious flash space.
Oh, I see.
In a RISC architecture, that same operation might require 4 separate instructions: load, multiply, store.
So that eats up 4 times the memory space.
Exactly. But as silicon fabrication advanced and flash memory got cheaper, the pure raw performance and power efficiency of the RISC single-cycle pipeline largely won out in the 32-bit embedded space.
Okay, so understanding the internal architecture, the Harvard buses, the bit widths, the instruction set density, is the vital underlying physics.
Right.
But how does the scale of these decisions change depending on who was making them? Because, an engineering student hacking together a prototype makes very different choices than a lead hardware engineer at a Tier 1 automotive supplier.
Oh, it's a completely different universe of constraints. And the sources highlight this beautifully through what we can call the $100 paradox.
Let's walk through the math of that paradox.
Sure.
If you are a hobbyist or an academic researcher, and you have a budget of $100 for your compute hardware, you're actually in an incredibly powerful position.
Very powerful.
For $100, you can buy a fully decked out development board, Arduino Mega, an ESP32 dev board with integrated Wi-Fi and Bluetooth antennas, or like a whole stack of Raspberry Pi Picos.
Yeah, you get a lot for your money.
You are buying highly integrated modules. You don't have to route the switching power supply inductors. You don't have to worry about the parasitic capacitance of your crystal oscillator traces. You literally just plug it in via USB.
And from my perspective in firmware, the ecosystem surrounding those $100 modules abstracts all the brutal silicon realities away.
Right. You don't have to look at the hardware.
You don't read the 1,200-page reference manual to find the exact memory address of the GPIO port register. The platform provides a hardware abstraction layer, or HAL.
Oh, it's just easy code.
Exactly. You just write digital write pin, HIGH, and the LED turns on.
But if you're listening to this and looking at DigiKey right now, you know there is a brutal ceiling to that abstraction.
A very hard ceiling. The $100 paradox is that while $100 buys a hobbyist a complete functioning ecosystem, that exact same $100 buys a professional and custom high-volume Mechatronics virtually nothing.
Wow.
It barely covers the shipping costs of the raw bare metal chips for a prototype run. To scale to industry level, you have to dig below the abstraction layer.
Let's make that real for a second. Take that Arduino board. It has a USB to serial bridge chip on it, maybe a CH340 or an FTDI chip, so you can program it easily.
Right, very common.
That chip costs about $2 in volume. If you are designing a custom PCB for a smart light switch that will be manufactured 10 million times.
Oh, man.
Yeah. Leaving that $2 convenience chip on your board just costs the company $20 million in bill of materials overhead.
You just can't do it.
You can't. You have to strip it away, buy the bare 50-cent microcontroller, and write the native USB protocol stack entirely in firmware.
And the stakes of that bare metal firmware change dramatically compared to the hobbyist world.
How so?
Well, in the hobbyist world, if your digital write command takes 50 clock cycles because the HAL is bloated with safety checks, it doesn't matter.
Right, it's just blinking an LED.
If it crashes, you press the reset button. But in the professional embedded world, we operate in real-time systems.
Which doesn't just mean computationally fast.
No, real-time means bounded and deterministic. It means the system is mathematically guaranteed to respond to an asynchronous physical event within a strict predefined time limit.
Which is known as the worst case execution timer, WCET, right?
Exactly. The sources divide this into a hard real-time and soft real-time.
Give me the physical stakes. What constitutes a hard real-time failure?
Hard real-time is a flight control system or the pressure relief valve controller in a chemical plant.
High stakes.
Incredibly high. Let's say a hardware interrupt fires, signaling a catastrophic pressure spike in a reactor vessel. The microcontroller might have exactly 10 milliseconds to execute the PID control loop and trigger the MOSFETs to open the relief valve.
Okay.
If it takes 11 milliseconds because the CPU is busy doing a garbage collection routine in memory or context switching to a lower priority task,
Too late.
the valve opens late, the pressure threshold is breached, and the plant explodes. The failure of the timing deadline is a catastrophic failure of the entire system.
That is terrifying.
Yeah.
And soft real-time.
Soft real-time is a consumer smart speaker. You ask it to stream a song over Wi-Fi.
Okay.
If the microcontroller drops an audio packet and delays the DXE output by 200 milliseconds, it's annoying. The audio stutters. The user might complain.
But nothing explodes.
Right. The system hasn't catastrophically failed. The quality of service just degraded.
So this is exactly why professional engineers cannot just pick whatever chip has the most GitHub stars. When an explosion is on the line, you don't guess. You need a rigorous, mathematically sound methodology to select your hardware.
Because the firmware can only ever be as deterministic as the underlying physical silicon allows it to be.
Which brings us to the core methodology detailed in the sources, the 10-step decision framework.
Right. How do we objectively filter 90,000 chips down to the single perfect silicon candidate?
Well, step one is establishing the absolute hardware foundation. You must start by creating a comprehensive hardware block diagram and an interface inventory.
That's crucial.
Before you even look at a vendor's parametric search engine, you have to draw the physical system. Every external sensor, every motor driver, every FPI flash chip, every wireless module.
Because the peripherals dictate the chip.
Exactly. And as a PCB designer, this is where I see projects immediately hit a brick wall. It's about pin counting and multiplexing conflicts.
Oh, the muxing conflict.
They are the worst. Let's say you draw your block diagram and you realize you have 12 distinct digital signals, 4 analog sensor lines, and a Wi-Fi module. That's 20 physical I/O pins.
Sounds simple enough.
So you think, great, I'll buy a tiny 20-pin QFN package.
But you can't.
You can't, because of power and ground pin.
Now you need power.
Exactly. 2 of those pins are VDD and ground, 2 more for the external crystal oscillator. Another 2 are dedicated to the SWD programming interface. You actually only have 14 usable GPIOs on a 20-pin chip.
That gets worse.
It does. Microcontrollers are incredibly dense, so manufacturers heavily multiplex internal peripherals onto the same physical external pins. Pin 15 might internally route to a standard digital output, or the analog-to-digital converter, or the transmit line for a UART serial port.
This is where you have to dive into the datasheet's alternate function mapping table.
Precisely. Because you might find a 32-pin chip that technically has 2 SPI ports and 2 UARTs.
On paper.
On paper. But when you map the physical routing for your PCB, you might discover that the high-speed clock line for SPI1 is multiflexed onto the exact same physical ball on the BGA package as the receive line for UART2.
Which means you can only use one or the other.
Right. If your system architecture requires both to operate simultaneously, you physically cannot route it. The chip is disqualified before you even look at its clock speed.
And part of this interface inventory is deeply understanding the electrical realities of the communication protocols you are demanding.
Yeah, the buses.
The sources break down the 4 foundational buses: UART, I2C, SPI, and CAN. If you misapply these, your hardware diagram is doomed.
Let's go through them, skipping the basic definitions and looking at the physical constraints. Take UART, Universal Asynchronous Receiver Transmitter. It's asynchronous, meaning there is no shared clock line between the 2 devices.
which immediately introduces the problem of baud rate drift.
Right. Explain that.
Because there's no clock line, both microcontrollers rely on their own internal oscillators to time the sampling of the bits.
Okay.
If one chip is sitting next to a hot power supply and its internal RC oscillator drifts by just 2% over temperature, by the time it samples the 8th bit of the UART frame, the timing window has completely misaligned.
Oh, man. So what happens?
You read garbage data.
So for UART, you often have to mandate an external temperature-stable quartz crystal in your hardware diagram, which adds cost.
Exactly.
Then we have I2C, the inter-integrated circuit bus. 2 wires, data, and clock, and you can address dozens of sensors. But from a hardware perspective, I2C is an open-drain architecture.
Let's explain why that matters for selection.
Okay, open drain means the microcontroller pins can only actively pull the voltage down to ground. To get a logical high, the bus relies entirely on passive pull-up resistors to slowly charge the parasitic capacitance of the physical copper traces.
Right.
If you run an I2C bus across a long cable or put too many sensors on it, the trace capacitance skyrockets.
And the signal degrades.
Exactly. The RC time constant becomes so slow that the voltage physically cannot rise past the logic high threshold before the next clock pulse hits. The bus collapses. I2C is strictly for short onboard communication.
And if you need high-speed data, like streaming raw bitmap data to an LCD screen, you need SPI, Serial Peripheral Interface.
SPI is a push-pull architecture. The microcontroller actively drives the line both high and low, meaning it can overcome parasitic capacitance incredibly fast. We're talking tens of megabits per second.
Fast, but it comes at a cost.
Yeah, it requires 4 dedicated wires and a separate chip select line for every single peripheral you add.
That adds up quickly.
If you have 5 SPI sensors, you need 9 physical routing traces, which makes the PCB layout a nightmare of length matching and crosstalk avoidance, especially at 50 megahertz.
And finally, CAN bus, Controller Area Network.
This is the heavy artillery. CAN uses differential signaling. Instead of measuring a voltage relative to ground, it transmits the data over 2 twisted wires, CAN high and CAN low.
Right.
The receiver only looks at the voltage difference between the two. Why? Common mode noise rejection.
Explain how that works in reality.
Well, if an industrial motor contactor slams shut or a spark plug fires, it creates a massive electromagnetic pulse. That pulse induces a voltage spike on both CAN wires equally.
Okay.
Because the receiver only cares about the difference between the two, the spike mathematically cancels out to 0. The data survives perfectly. If your block diagram involves long cables and noisy environments, CAN is non-negotiable.
So once you have established your hardware block diagram, resolved your muxing conflicts, and locked in your physical bus protocols, we move to steps 2 through 4. Identifying data assets and establishing memory floors. We have the physical roads. Now we need to know the payload and the required warehouse space.
Are we just filtering an analog voltage, or are we calculating cryptographic hashes?
Exactly. You have to estimate the processing core requirements, and more importantly, calculate the hidden memory traps.
Ah, the hidden traps.
This is where I see hardware teams select a chip, hand me the prototype, and I have to tell them the project is dead.
Because they underspec the flash or the RAM. Walk us through how a memory floor calculation actually works in practice.
Let's say you are building a smart commercial door lock.
Right.
The core application logic reading an RFID card via SPI, checking an array of valid IDs, and toggling a GPIO to trigger the strike relay is tiny.
Very simple.
That bare metal logic might compile down to 8 kilobytes of flash memory and use maybe 2 kilobytes of SRAM for variables. The hardware engineer looks at that and selects a 32 kilobyte MCU to be safe.
Which seems entirely reasonable on paper.
Until marketing dictates that the lock must be configurable via a smartphone app.
Oh boy. Feature creep.
Massive feature creep. Now you have to integrate a Bluetooth low energy, a BLE stack.
That's not small.
Not at all. A BLE stack is not just a simple driver. It is a massive, highly complex OSI model software architecture.
Right.
It requires a link layer state machine to maintain microsecond accurate connection intervals. It requires the L2CIP layer for multiplexing. It mandates AES-CCM cryptographic integration for pairing security.
The encryption libraries alone are huge.
Massive. The pre-compiled vendor BLE library might consume 130 kilobytes of flash immediately.
Wow.
Furthermore, to manage the timing constraints of the radio without dropping the physical motor control tasks, you are forced to implement an RTOS, like FreeTOS or Azure ThreadX.
And an RTOS isn't free.
Far from it. An RTOS requires a task control block, a TCB in SRAM for every single concurrent thread, plus a statically allocated stack space for each thread so they don't overwrite each other during context switches.
Makes sense.
The RTOS kernel itself takes up flash. So your 8 kilobyte application suddenly sets a hard minimum architectural floor of 256 kilobytes of flash and 64 kilobytes of SRAM just to successfully compile and boot.
So if you bought that 32 kilobyte chip,
You are completely stuck.
okay, so through steps 1 to 4, we have drawn our physical hardware,
Right.
we've untangled our pin muxing, we've validated our bus topologies, and we have established our hard memory floors.
We've done a lot of filtering.
We have. We have taken that DigiKey list of 90,000 chips, maybe filtered it down to a few hundred, but we still have to pick one.
Right.
How do we make that final objective decision without relying on gut feel? This brings us to part 4 of the framework, the Kepner-Trego matrix and the concept of showstoppers.
Let's talk about showstoppers first because they act as the ultimate physical filter.
Define a showstopper for me.
A showstopper is an absolute non-negotiable project requirement that instantly eliminates 90% of the silicon market. You don't even evaluate a chip further if it fails a showstopper.
The classic example from the sources, and one I deal with constantly in hardware, is the operating temperature range.
Oh, that's a big one.
Huge! Commercial-grade microcontrollers are rated for an ambient temperature of 0 to 70 degrees Celsius. But if you are designing an engine control unit that will be bolted under the hood of a truck,
70 degrees Celsius is nothing under a hood in the summer.
exactly, you need an industrial temperature rating, which is negative 40 degree to plus 85 degrees C, or an automotive rating up to plus 125 degrees C.
And this isn't just a marketing label?
No, it's semiconductor physics. At negative 40 degrees Celsius, the equivalent series resistance, the ESR of your external decoupling capacitors, completely changes.
Right.
The internal phase-locked loops, the PLLs that multiply the clock frequency, they might fail to lock.
Which means no clock.
No clock. The carrier mobility of the electrons in the silicon substrate shifts so drastically that setup and hold timing constraints inside the CPU are violated, and the chip simply will not execute instructions. If the datasheet doesn't guarantee negative 40 to 125 C, it's a showstopper. It's out.
Another major showstopper mentioned is AEC Q100 automotive qualification.
Right.
An MCU might have the right temp rating, but if it hasn't survived the brutal AEC Q100 stress testing, which includes extreme thermal cycling to check for package delamination and latch-up testing, where they literally inject current into the pins to see if the internal parasitic transistors short out, you cannot legally put it in a vehicle's braking system.
Are there firmware showstoppers too?
Oh, definitely. Hardware cryptographic accelerators are a prime example.
Okay.
If your medical device mandates AES 256 encryption for data at rest, and you try to calculate that in software on an 8-bit chip, it will take seconds per block and drain the battery. You need a dedicated silicon crypto engine. If it doesn't have it, showstopper. Out.
So the showstoppers aggressively filter the list down from a few hundred down to maybe 3 or 4 highly qualified candidates. Now we have to objectively rank them. We build the Kepner-Trego matrix. The KT matrix.
Right. The KT matrix is a structured methodology for eliminating conscious and unconscious engineering bias.
Because we all have bias.
Exactly. As engineers, we inherently have bias. I might say, I really want to use this specific NXT chip because I already have the build environment set up on my laptop, and I don't want to learn a new vendor's register mapping.
Makes sense from your perspective.
Sure, but that NXP chip might have an atrocious supply chain lead time and cost twice as much. The matrix forces objectivity.
The mechanics of it are actually really straightforward. You gather the cross-functional team and define your evaluation categories. Unit cost, software ecosystem quality, power consumption, security features, stuff like that.
Right.
Then you assign a weight to each category from 1 to 5 based on the product's business goals.
Give me an example.
Well, if it's a disposable smart bandage, cost is a 5. If it's a hardware authentication token, security is a 5. You score each MCU candidate in each category, multiply by the weight, sum of the columns, and the highest number is your mathematical winner.
It creates a clear, defensible paper trail for the architecture decision.
But let me push back on this because I've sat in these meetings.
Oh, I'm sure you have.
What happens when it becomes a political weapon? Management comes in, hyper-focused on the bill of materials, and demands that cost is weighted as a 5.
A classic scenario.
Right. And the engineering team desperately wants software ecosystem to be a 5 because they know from experience that the ultra-cheap silicon has broken compiler tool chains and 0 community support. Doesn't the matrix just get manipulated to give management the cheap chip they wanted anyway?
That's a very real scenario. But if we connect this to the broader realities of engineering management, the KT matrix actually neutralizes the politics by forcing absolute transparency regarding the trade-offs.
How so?
Let's say management forces cost to a 5, and the cheapest microcontroller wins the matrix. 6 months into development, the firmware team is completely stalled because the cheap chips vendor provided a buggy I2C driver, and there's no technical support forum to ask for help. When management asks why the project is delayed and burning cash, the engineers pull up the KT matrix. They can say, look right here, we scored this chip's ecosystem a 1. We mathematically warned you that this was the visible trade-off of forcing costs to a 5.
Oh, I love that. It instantly quantifies the hidden pain of cheap silicon.
It makes the downstream consequences visible at the start line.
That is brilliant. But even with the matrix, the sources point out that the numbers can lie if you don't account for real-world manufacturing physics and actual firmware realities.
Which brings us to part 5, trade-offs, traps, and the realities of production.
Right. The first massive trap we have to discuss is the underutilization fallacy.
This is a psychological trap that almost every beginner and even some intermediate engineers fall into.
What is it?
They look at a highly constrained problem, say reading a single analog water pressure sensor once a minute and toggling a local relay.
Super basic.
They look at a powerful 32-bit, 100 megahertz ARM Cortex-M4 and they feel physically guilty. They think, that's massive overkill. It's computationally wasteful. I should architect this using a tiny 8-bit 10 megahertz chip.
Okay, wait. I'm going to challenge that immediately.
Go for it.
As a hardware designer responsible for the BAM cost, if I can buy the 8-bit chip for 90 cents and the 32-bit ARM chip costs $1, why on earth would I spend $1 to monitor a water sensor?
Because of the software side.
But saving 10 cents on a production run of 100,000 units is $10,000 directly to the bottom line. It sounds like lazy engineering to overspec the part just because it's easier.
On paper, in a vacuum, you are right. But here is the brutal reality of professional firmware engineering. Silicon performance is incredibly cheap, but developer time is exorbitantly expensive.
Okay.
Let's look at your 10-cent savings. Yes, you saved $10,000, but because that 8-bit chip is so highly constrained, it lacks an advanced floating point unit and doesn't have modern vendor-supplied hardware abstraction libraries.
So the firmware takes longer to write.
Exponentially longer. To process that analog sensor data accurately, the developer has to spend 2 months manually optimizing the fixed-point math routines in custom assembly code to prevent overflow errors.
Wow.
2 months. And they have to write the ADC register drivers from scratch. 2 months of a senior embedded engineer's fully loaded salary and benefits vastly outweighs the $10,000 you saved on silicon.
That actually makes a lot of sense.
And that doesn't even factor in the opportunity cost of delaying the product launch by 8 weeks. In the professional world, unless you are building hundreds of millions of units, you buy the $1 chip, finish the application code in a week using high-level C++ and vendor middleware, and you ship the product.
So underutilization is a myth. Fast, reliable time to market is the reality.
Exactly.
That is a massive perspective shift. The goal isn't to optimize the silicon. The goal is to optimize the total project cost, and developer time is the most expensive component. Another major trap the sources highlight, which directly ties into our story at the beginning of the deep dive, is hardware peripherals versus bit banging, and the critical importance of DMA.
Oh, let's define bit banging first, because it is the ultimate desperate workaround.
What is it?
Bit banging is using pure software loops to manually toggle a general-purpose I/O pin high and low to emulate a complex communication protocol.
Give me an example.
Let's say your hardware block diagram dictated 2 hardware SPI ports. But late in the design phase, you realize you need a third SPI sensor, and the chip you selected only has 2 dedicated SPI peripherals.
So instead of spinning a new board with a bigger chip, the firmware engineer writes a function that says, turn pin 4 high, run a delay loop for exactly 1 microsecond, turn pin 4 low.
Yes.
You are manually creating the clock signal with CPU instructions.
Yes, and it's incredibly dangerous. First, it wastes millions of CTU cycles just sitting in empty NOP loops to generate delays.
Right.
But more catastrophically, it completely destroys your timing determinism because of interrupt jitter.
Explain interrupt jitter in this context.
The CPU is in the middle of executing your bit-banged SPI code, meticulously timing a 1 microsecond clock pulse. Suddenly, an asynchronous hardware interrupt fires.
Like what?
Maybe the user pressed a button or a timer overflowed. The CPU immediately halts the SPI function, pushes context to the stack, and jumps to the interrupt service routine.
Okay.
By the time it finishes handling the button press and returns to your SPI function, 15 microseconds have passed.
Oh no.
Your carefully timed 1 microsecond clock pulse just stretched to 15 microseconds. The timing is violently corrupted, the sensor misreads the data, and the bus locks up.
Which is exactly why you need dedicated silicon peripherals that handle the protocol autonomously. And more than just the peripheral, you need DMA, direct memory access.
DMA is the great liberator of the embedded CPU.
I always visualize the CPU as the central train dispatcher in a massive rail yard.
I like this analogy.
Without DMA, every time a cargo train, say a byte of data from an SPI ADC arrives at the station, the dispatcher has to stop managing the overall network, walk down to the track, manually unload the cargo box, and carry it into the SRAM warehouse.
Sounds exhausting.
Right. If data is coming in at 10 megabits per second, the dispatcher does nothing else but carry boxes. The entire system grinds to a halt.
The CPU is 100% utilized just moving data.
But DMA acts as an autonomous, programmable rail switch. You configure it once at boot up. You tell the DMA controller, listen to the SPI peripheral. Every time a byte arrives, automatically switch the internal data bus, steal one single clock cycle, and route that byte directly into a specific array in the SRAM warehouse.
So the CPU doesn't have to do it.
Exactly. The CPU doesn't even look up from the control board. The DMA handles all the low-level data movement perfectly in the background. The CPU is completely free to run complex navigation algorithms or update the display.
And only when the buffer is full does it notify the CPU.
Right. Only when the entire 1 kilobyte buffer is full does the DMA tap the CPU on the shoulder with an interrupt.
If you are doing anything involving high-speed data audio streaming, display driving, high-frequency sampling, and your chosen microcontroller does not have robust DMA architecture with bus matrix arbitration to handle cycle stealing, your project will fail.
The CPU will drown in its own interrupts.
Exactly. And while we are talking about memory architectures crashing the CPU, we have to tackle the most notorious firmware trap of all, the danger of the heap.
Oh, right. Why do seasoned embedded engineers look at dynamic memory allocation, the malloc, function like it's radioactive?
Because in a deeply embedded, memory-constrained environment, dynamic allocation is a ticking time bomb of fragmentation.
How does it work on a normal computer?
In desktop programming, if you need a buffer to store an incoming string of text, you just call malloc to allocate memory dynamically on the heap. When you are done, you call free to release it back to the system. You do it millions of times a day.
Because you have huge memory.
Right. Desktop computers have 16 gigabytes of RAM and massive OS-level virtual memory managers that handle garbage collection.
And a microcontroller might only have 32 kilobytes of physical SRAM total.
Exactly. The RTOS memory manager handles the heap by maintaining a linked list of free blocks. Imagine your 32 kilobyte RAM is a pristine, solid block of cheese.
Okay, cheese, I'm with you.
Every time you allocate memory, the manager cuts out a slice. When you free it, it puts a slice back. But over time, as variables of wildly different sizes, a 12-byte string here, a 128-byte packet there, are created and destroyed in random order, you don't have a solid block anymore. You have Swiss cheese.
Heap fragmentation.
Yes. You might have a total of 10 kilobytes of free memory remaining, but it's shattered into hundreds of tiny disconnected 10-byte holes scattered across the RAM.
And then a network task asks for a contiguous 50-byte block of memory to assemble an MQTT packet.
And the allocation fails. The manager traverses the entire linked list, can't find a contiguous 50-byte block, and malloc returns a null pointer.
And if the code doesn't handle that?
If your C code isn't rigorously written to check for and gracefully handle that null pointer, which is extremely difficult to test for completely, the microcontroller attempts to write to memory address 0, triggers a hardware fault, and instantly hard crashes.
That is terrifying. And the truly terrifying part of fragmentation is that it is a function of time.
Yes, it is.
Your testing in the lab over a 48-hour burn-in period looks perfectly fine. But 90 days after you deploy 1 million smart environmental monitors to the field, the entropy of the heap finally reaches critical mass, and they all start randomly rebooting.
This is exactly why safety-critical domains like aviation DO 178C standards or automotive ISO 26222 strictly forbid the use of the heap.
They mandate static allocation.
Absolutely. All the memory for every global variable, every buffer, every RTOS task stack is statically reserved at compile time in the BSS and data segments. The compiler calculates the exact physical address of every byte before the code ever runs on the silicon.
If you don't have enough RAM, the program simply refuses to compile.
Right. Or if they must use dynamic allocation, they use memory pools.
How do those work?
Block allocators. Instead of arbitrary sizes, the RAM is pre-divided into fixed uniform pools, say 50 32-byte blocks and 10 128-byte blocks.
Okay.
When you request memory, you get an entire block guaranteeing an O1 deterministic allocation time and absolutely zero external fragmentation.
I want to pivot back to hardware for a second because these sources provide an incredible case study of what happens when you throw all of this theoretical elegance out the window and optimize for raw, BOM, cost above absolutely everything
Oh,
else.
the restaurant pager.
Yes, it's a hardware teardown of a cheap restaurant pager.
You mean the coasters that buzz and flash red LEDs when your table is ready?
Exactly. When engineers tore one of these down, they found it was driven by an 8-bit STC15F204EA microcontroller.
A modernized variant of the ancient Intel 80501 architecture.
Yes, and it is incredibly brutally cheap.
Hmm.
But what blew my mind wasn't the chip. It was the PCB layout decisions dictated by the cost of the chip.
Oh, this is great.
To save fractions of a cent on manufacturing millions of these pagers, the designers avoided standard, slightly more expensive PCB fabrication processes.
Specifically, they didn't pay for tented vias.
Right. Let's explain why that's insane. A via is a small copper-plated hole drilled through the fiberglass board to electrically connect a trace on the top copper layer to a trace on the bottom layer.
Very standard.
Standard industry practice is to tent the via, meaning the manufacturer covers the exposed copper hole with the green solder mask polymer to electrically insulate it. It prevents accidental shorts.
But it costs money.
Adding that solder mask tenting step across the board costs a tiny fraction of a penny per unit. So the pager designers didn't tent them. They left the exposed metal via holes completely bare, right on the top layer, directly underneath other surface mount components.
Which is an absolute recipe for a short circuit, particularly with the crystal oscillator.
Yes, the crystal oscillator is a small metallic can that provides the precision, high-frequency heartbeat clock signal for the microcontroller.
And it was sitting right on top of a via.
The metal bottom of that oscillator package was sitting directly over an exposed, untented via carrying a different signal. The parasitic capacitance alone would ruin the clock signal, but worse, if the metal can touch the via, it would short out the entire board.
So how did they solve it without paying for the tenting?
The manufacturing facility literally, physically, tilted the crystal oscillator sideways.
That's kidding.
No. They soldered them on an awkward 45-degree angles so the metal can hovered in the air, physically suspended above the exposed traces. It looks like a manufacturing defect, but it was a calculated, brilliant, horrifying piece of extreme, high-volume mechatronics.
Wow. It perfectly proves the point that sometimes, at the extreme edges of volume, the microcontroller selection and the entire system architecture are dictated entirely by the brutal physics of how cheaply you can manufacture the physical board around it.
But as we transition into Part 6 of our framework ecosystems, supply chains, and engineering instincts, we have to acknowledge that for 95% of applications outside of disposable pagers, the raw hardware cost is actually dwarfed by the software lifecycle and the supply chain.
This is perhaps the most critical realization in modern embedded engineering. The raw specifications of the silicon itself, the clock speed, the flash size, don't matter nearly as much as the support ecosystem surrounding it.
Explain that because it sounds counterintuitive to a hardware designer. If the chip has the right specs and passes the showstoppers, why does the ecosystem matter?
Because a highly spec'd MCU without mature compilers, without native RTOS integration, without solid, bug-free hardware abstraction layers, and without an active developer forum is a waking nightmare.
You're just fighting the tools.
You will spend 80% of your development cycle fighting the silicon manufacturer's undocumented register behaviors instead of writing your actual product application.
The sources specifically call out modern ecosystems like Renesas FSP, the Flexible Software Package, or STMicroelectronics Cube ecosystem.
Yes. These ecosystems provide a massive graphical configuration tool and a layer of highly tested, pre-written middleware. They allow developers to write hardware-agnostic logic.
How does that help?
Well, if I write my motor control application using a well-architected HAL provided by the ecosystem, and I suddenly discover I need a faster hardware timer, I can just change a drop-down menu in the configurator.
And it updates the code.
The tool regenerates the low-level register initialization code automatically. I can even port my entire application to a completely different MCU within the same vendor family, and my high-level C++ code barely has to change. The ecosystem provides the translation layer that protects developer time.
And before you commit to a vendor's ecosystem, the framework insists on Step 8. Prototyping. You absolutely must buy a vendor evaluation board, a dev board, to prove the ecosystem actually works before you design custom hardware.
You never, ever design a custom PCB based solely on reading a 2,000-page datasheet. Datasheets have errata documents, they have misprints. Features that work on paper have subtle hardware bugs in specific silicon revisions.
This brings up one of my favorite analogies from the embedded manifestos in our sources. Skipping the dev board and going straight to custom PCB routing is like bungee jumping.
You get one shot, and if the cord is too long, you hit the ground.
Exactly. Let's look at the physical reality of a modern 32-bit MCU. It likely comes in a BGA package, a ball grid array.
Right.
There are no exposed pins extending from the sides of the chip. The connections are hundreds of microscopic solder balls hidden completely underneath the silicon package. You physically cannot reach them with a soldering iron to make a modification. You can't even probe them with an oscilloscope to debug a signal.
BGAs require incredibly complex PCB fabrication. We are talking 4 to 6 layer boards minimum, requiring high-density interconnects, blind and buried via controlled impedance routing.
It costs thousands of dollars just to fabricate the bare boards, let alone the automated pick-and-place assembly.
Yeah, it's not cheap.
So if you skip buying the $100 dev board to test the vendor's erratic I2C hardware, and you spend $5,000 in 4 weeks fabricating a custom 6-layer BGA motherboard, and you make one fatal, unpatchable hardware error based on a misread datasheet.
Oh, that hurts to think about.
Say you accidentally route a critical interrupt line to a pin that is marked Do Not Connect in the errata document.
You can't fix that with an X-Acto knife and a jumper wire. The mistake is buried in the inner layers under the chip.
The board is completely dead. You throw away the $5,000 and you lose a month of schedule.
Mm.
Always buy the dev board. Wire up your critical sensors with jumper cables on your desk. Prove the high-risk peripherals and the DMA channels work in firmware before you authorize the PCB fab run.
And that leads perfectly into the final, massive reality check of the modern era, step 7 in the selection matrix, supply chain resilience.
Oh, the 2024 to 2026 post-shortage reality. The global chip shortage radically, permanently changed how hardware engineers approach design.
It really did.
We had to completely abandon the just-in-time manufacturing philosophy where components arrived on the loading dock the day before assembly and moved to inventory as a buffer.
You simply couldn't trust lead times anymore. A standard microcontroller that usually took 6 weeks to order suddenly had a 52-week or even 104-week lead time.
It was chaos.
I saw entire production lines shut down, millions of dollars in revenue lost, because a 50-cent I2C expander chip was globally out of stock.
So how did that trauma change the engineering mindset for selecting MCUs?
It forced the entire industry into defensive engineering. The ultimate instinct for an experienced embedded engineer now is paranoia.
Paranoia. I like that.
From a firmware perspective, you never tightly couple your core application logic to one specific vendor's proprietary hardware registers. As we discussed with the HALs, you must write highly portable abstracted C or C++ code.
Because chips disappear.
Because if your primary ST microelectronics chip goes globally out of stock, you need to be able to port your application to a microchip PIC32 or a NXP chip in a matter of weeks, not months.
And defensively, from a hardware layout perspective, we started intentionally designing Swiss cheese PCBs.
Explain that.
If we had the physical board space, we might put down 2 entirely different footprint patterns for 2 different microcontrollers from different vendors on the exact same board.
Oh.
Yeah, they share the same peripheral routing. At the factory, the pick-and-place machine only populates one of them. But if chip A goes out of stock,
Yeah.
we don't have to redesign and requalify the whole PCB. We just buy chip B, change the bill of materials, and solder it to the alternate pads.
And crucially, tied to that flexibility, you must always plan for an over-the-air or OTA bootloader.
Right.
If you are forced to swap to a different silicon revision or a different MCU entirely in the middle of a production run to keep the lines moving, you need a robust, cryptographically secure way to push updated firmware binaries to those new devices once they are deployed in the field.
The bootloader is your final safety net.
Always.
So we've covered the internal architecture, the real-time stakes, the block diagrams, the hidden memory floors, the matrix, the DMA traps, and the supply chain paranoia. How do you take all these rules and turn them into gut instinct? We're coming to the end of our deep dive, and we need to summarize the core approach for building this capability.
It's entirely about reps. You build the instinct by starting small and obsessing over the
You
details.
got to put in the work.
You read data sheets meticulously, not just the glossy first page, but the boring electrical characteristics tables and the errata documents at the very back. You force yourself to use the 10-step framework on every project, even the simple hobbyist ones.
Because practice makes perfect.
You build KT matrices until evaluating the trade-offs between physical I/O pin multiplexing, RTOS static memory floors, and supply chain lead times just becomes second nature.
You learn to see the matrix. You learn to instinctively balance the physical, tactile constraints of the hardware layout with the logical, sequential constraints of the firmware.
But just as you feel you've mastered this framework, the industry shifts beneath our feet again. Which brings us to a final, highly provocative thought derived directly from the sources.
Right. We noted earlier in the source material that designing a cutting-edge 10-nanometer custom ASIC chip now costs upwards of $170 million in NRE. Pushing to 5-nanometer is over $500 million.
That is just an astronomical cost.
It is. And that physical fabrication cost is pushing tech giants to develop highly specific custom silicon only for massive data centers. But it is driving the rest of the embedded industry to integrate neural processing units, NPUs, directly into standard off-the-shelf microcontrollers.
The massive shift toward edge AI. We are seeing standard Cortex-M chips shipping with dedicated silicon matrix multiplication accelerators.
Exactly. And this raises an incredibly important question for you to mull over as you design your next hardware architecture.
Yeah.
In the next 5 years, as embedded devices shift from running traditional, deterministic if and procedural C code to evaluating highly trained neural network tensor models right there on the edge.
It changes everything.
It does. Will the microcontroller of the future even execute traditional software as we know it? Or will it just become a massive physical brain synapse, a mesh of SRAM weights, simply waiting for analog sensory inputs to trigger a probabilistic response?
Think about how that paradigm shift will radically change how you draw your hardware block diagrams.
The memory alone.
The memory requirements just to hold the inference weights will be staggering. The power delivery networks will have to handle massive dynamic current spikes during tensor evaluations. The entire framework will have to evolve.
The illusion of simplicity on the outside of the device is only going to require infinitely more complexity under the hood. Thank you so much for joining us on this deep dive.
It's been great.
We hope this framework helps you navigate the 90,000 choices out there, protects your DMA channels, and saves you from at least a few million-dollar engineering nightmares. Keep exploring your sources, keep questioning those datasheets, and we'll catch you on the next one.